Hello and welcome back. So in the last video we discussed about convolution. Hello and welcome back. So in the last video we discussed about convolution, and we discussed that if we take the Laplace inverse of two functions, the product of two functions fs and gs, this is equal to, so you evaluate the Laplace inverse of first function, Laplace inverse of second function, and the Laplace inverse of product is going to be the convolution of ft, or you can say convolution of f with g. This important property we talked about in the last section, and using this property we saw how to find out Laplace inverse. We worked out on some examples. In this video we are going to start with how we solve ODEs using the convolution. Okay, so let's start. So first example we are going to see is this one. If we have x double prime plus x equal to sine t. This we worked before also, but now using the convolution we will see how easy this is. Okay, and the initial conditions are the value at 0 and the value of derivative at 0 is equal to 0. So our first step is always the same. So the basic idea is always the same. We take the Laplace transpose, we solve for xs, and then we take Laplace inverse. Okay, so we take the Laplace transpose for x double prime. We have s square xs minus x of 0, sorry, s times x of 0 s times x of 0 minus x prime 0. This is the value for Laplace of x double derivative, and then we have plus Laplace of x, which we are denoting by xs, right? So this is Laplace of x, xt, and this is equal to Laplace of right hand side, which is sine t. So here we are not going to evaluate the Laplace of right hand side. You can keep it as it is also if there is only one function. Okay, you can keep it as it is. Basically we are not going to evaluate our right hand side. So x of 0 is 0, so this term is 0. X prime at 0 is 0, so this term is 0. So in the right hand side we have s square plus 1 times xs, and in the right hand side we have Laplace of sine t. So we solve for xs and we get Laplace of sine t divided by 1 s square plus 1, or 1 plus s square. Now using the table, Laplace of, so this is some separate information just to recall, Laplace inverse of s square plus 1 is equal to 1 over s square plus 1 over s square plus 1 is equal to sine t. So basically here we have the product of two functions. So this is equal to Laplace of sine t times Laplace of sine t, the product of Laplace. So now if we take Laplace inverse both sides, taking inverse Laplace, we get, in the left hand side we will get xt, in the right hand side Laplace of product, Laplace inverse of product of two functions is basically the convolution of those two functions. So we have convolution of sine t with sine t, right? And convolution is defined as integration from 0 to t sine xi times sine t minus xi t xi, right? This is just the definition of convolution. And now we are going to use a trigonometric identity, which is 2 times sine A sine B is equal to cosine of A minus B minus cosine of A plus B. So we are going to use this identity over here. So what we'll get is, let me change the color of my pen. So what we will get is, we don't have a 2 multiplied, so we will multiply by a 2 and we will divide by 2. And then we will use this identity and we will get 1/2 integration from 0 to t sine, we subtract the angle, so we have xi minus t minus xi. So 2 xi minus t, cosine, should say cosine, minus cosine of sum of the angle, which is going to be t d xi, right? So we have 1/2 cosine integration is sine 2 xi minus t, and we divide by the coefficient of the variable we are integrating with respect to. So we divide by 2 minus, we are integrating with respect to xi, so cosine t is a constant. So integration of constant is constant times xi, and the limits are from 0 to t. Substitute the upper limit first. So we have 1/2 2t minus t, so sine t divided by 2 minus t times cosine t, and then we substitute the 0, the lower limit. When we substitute 0 in the first term, we will get sine of minus t, which is okay, let me write it down. Sine minus t divided by 2, and the second term is 0 because we have xi multiplied, so it's 0, which is equal to 1/2 sine t divided by 2 minus t times cosine t. Sine is odd function, so sine negative t is negative sine t. Negative negative will be positive. So what we got is our xt is equal to 1/2 sine t half plus sine t half is sine t minus t times cosine t. And this is our answer. So this is how we solve ODEs using the convolution. So previously when we were taking the Laplace inverse of this function, we need to involve the partial fraction, but now since we have convolution technique, we can directly do it. So convolution makes it easier to solve the ODEs. Next we are going to discuss about our last topic in this chapter, which is Volterra equation. Volterra integral equations. This is last topic of this chapter, and these equations are very important in general. And a Volterra equation looks like xt equal to ft plus 0 to t g t minus xi times xt dt. This dxi. These two functions are dxi. xi dxi. Okay. And here the function ft and the function g are known function. We already know what they are, and we wanted to solve for xt. So this is the form of Volterra integral equation. We know the function f and g, and we want to solve for xt. Let's see an example how we solve Volterra integral equations using convolution. So our first example is to solve xt equal to cosine t plus 0 to t cosine of t minus xi x xi d xi. So what we are going to do is we are going to apply the Laplace. The technique in this chapter is the same. We apply the Laplace, we solve for x's, and then we take Laplace inverse. So if we apply the Laplace, what we get is, in the left hand side, Laplace of xt is xs, Laplace of cosine t is s divided by s square plus 1 plus. Now this is convolution. This right hand side over here, this function is convolution of cosine t and x t. So basically in the Volterra equation, our second term is convolution of g and x. So what is the Laplace? So Laplace of convolution is the product of the two Laplaces, right? So this is going to Laplace of first function, Laplace of cosine t. Okay, let me write down in one more step, times Laplace of xt. So basically our xs is equal to s divided by s square plus 1 plus Laplace of cosine t is s divided by s square plus 1 and Laplace of xt we denote it by xs. So we want to solve for xs, so we move the second term to the left hand side. So 1 minus s divided by s square plus 1 times xs is s divided by s square plus 1. S square plus 1 minus s divided by s square plus 1 x s is s divided by s square plus 1. We divide by the coefficient of xs both sides, and what we'll get is xs equal to s square plus 1. The right hand side is s divided by s square plus 1 times s square plus 1 divided by s square plus 1 minus s. S square plus 1 we can cancel it out. So we have right hand side is equal to s divided by s square plus 1 minus s. And our last step is we take the Laplace inverse. So we want to find out the Laplace inverse of right hand side. Okay, let's find out the Laplace inverse of right hand side. So what we are going to do is we are going to use completion of squares for the denominator. So s square plus 1, s square minus s plus 1. We add and subtract the 1/2 coefficient of s. So coefficient of s is 1, negative 1. We divide it by 2, so 1/2. So we add 1/2 square and we subtract 1/2 square. So from first three terms we get s minus 1/2 square, and from this term you will get 5/4, right? No, sorry. So this is 1/4, negative 1/4 plus 1. So we will have plus 3/4. Okay. And so we have Laplace inverse of s divided by s minus 1/2 square plus 3/4. If you will see this function carefully, this resembles with the Laplace inverse of cosine t. But in the denominator we have s minus half, and in the numerator we just have s. So what we can do is, we can write it as Laplace inverse of s minus half divided by s minus half square plus 3 over 4. So we are basically adding and subtracting 1/2 in the numerator. S minus 1/2 square plus 3 over 4. And we are using the property of linearity. Okay, so the first term gives us cosine t, but then there is a shift. The shift is by 1/2, right? So we have cosine t minus, cosine of 3 over square root 3 over 2. So this is equal to cosine of square root 3 over 2 t minus, there is a shift, right? So if there is a shift, we multiply the function, this is eraser, not my pen. We multiply the function by e power that shift. So we multiply the function by e power 1/2 t plus, in the second one, this resembles with the Laplace inverse of sine, but then in the numerator we should have omega if 3 over 4 is omega square. So what we are going to do is, we pull out the 1/2, we multiply by square root 3 over 2 and since we multiplied by the square root 3 over 2, we multiply it over by square root 3 over 2, so we should divide by square root 3 over 2, which will be 2 over square root 3. So what we'll get is e power 1/2 t cosine of square root 3 over 2 t plus 2 over square root 3 sine of square root 3 over 2 t. This is our solution. Okay. Very simple, right? And in this step over here, we used the property, shift property. So the steps are simple. Every time we want to use Laplace transform to solve a ODE, we first take the Laplace transform, we solve for xs, and then we take the Laplace inverse. There are more worked out examples based on Volterra equation in the notes. Go ahead and look over those examples also and practice more and more problems. Only practicing the problems can make you understand these concepts very well. And we'll stop here today, and this was our last lecture for introductory ODE class, and if you have any doubt you can contact me. Bye bye. Take care, practice more and more problems.